Good. How are you? Staying cool?
I love the heat. I'm happy it's here. I live in California.
And now summer came early, very early for the seat.
Yeah, usually this happens in July, August.
Yeah, yeah.
I appreciate it. I missed it when I was working electrical as an electrician in Washington,
Oh,
and it was 17 degrees outside.
yeah.
It was a rough end, so it was just plywood, nothing
Oh my
else. You're just
gosh.
touching, obviously, the electrician, you're touching metal all day, so
Yeah.
and you have no dexterity in your hand.
Oh my gosh. Oh, that sounds awful.
Yeah, it was. I missed the weather for sure. I wasn't in an office, so.
Yeah.
Um, see it's what is it? I'm gonna, what does it entail as far as being part of it? Because I don't want to be a part of it. Right.
It's not a frat. I know that's the thing people say. Basically it's an honor society basically. So you kind of join, and I'll be honest with you. So I joined when I was in college and kind of forgot that I was a member for a long time. And then I started working here, and then they needed an advisor, and they looked me up and they said, "Oh, you're Talbot Pi." I was like, "I am in Talbot Pi." But it's mostly just so it's something you put on your resume basically, so that you said you're part of it. Certain employers that are also that value that will have that will look highly on that too. So yeah, it's and there's benefits too, like you can apply for scholarships, things like that. So,
Specifically for that, for this group essentially.
yeah. Yeah. Mhm. Yeah. So the Talbot Pi, they're a national society, so they collect membership fees and stuff, and they basically give that back in the form of scholarships. So it's a one-time fee you pay just now, and then you're a member for life.
How much is the fee?
It's I'll have to check with my officers because or you can email Jessica and see. So Jessica's our president this year. I think it's like around 80 or 90. I think that's what it is.
All right.
Mhm.
Thank you.
Mhm. All right, it's 4 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. Okay, so today we're going to finish up our discussion on divergence theorems. I apologize, we're a little bit behind. And so I know that you guys are waiting for the divergence stuff just so you can do the last homework assignment. So we'll finish that up today. Thankfully, divergence theorem, at least for what we're going to use it for, is not too bad. I think problem 5 will probably be the one you spend the least amount of time on the homework. So we'll do an example today, kind of show you what it is, but there's really not much to it. Because we're kind of skipping the time consuming part of it, which is the surface integrals. But but the triple integral part usually is not too bad. Okay. After that, we are moving on to our next topic here, which is Fourier. So it's kind of a big shift. And so, we kind of spent the last couple of weeks talking about multivariable calculus, and then we're doing something completely different after that. So, I think I mentioned kind of after the first midterm, this is the part of the class where I think it's you get a little bit of whiplash because we're just kind of changing between topics very rapidly. But Fourier is kind of the next important thing to know. Okay. All right, so other announcements. So I brought the midterms again today. So if you didn't get a chance to pick up your midterms on Tuesday, you can do that again after class today. Today will probably be the last time I bring the exams to the lecture. And so if you are not able to pick it up after class today, they will be in my office. And so you'll have to come to my office and pick up your exam. Okay. All right, any questions I can answer before we get started? Okay, all right, so let's go ahead and get started. Okay, so the last topic that we have in this unit of vector calculus is this idea of the divergence theorem. Okay. So divergence theorem we use it in a very similar way as Green's theorem, where essentially we're using it as a method to transform an integral. And in particular, for divergence theorem, we're looking to transform between a surface integral and a triple integral. Okay, so the form for divergence theorem looks like the following. And so on the one hand, we have our surface integral. Okay. All right, so this looks very similar to our Green's theorem, where Green's theorem we had a line integral on one side. This time we have a surface integral. Okay. Right. So this right here, this is a surface integral on a closed surface. Right, the key word there being closed, just like in Green's theorem. So we'll go over what that means in a second. And on the other side here, we have a triple integral. Okay. A triple integral of the divergence of the same vector field on that same boundary or the same kind of domain as on the left-hand side. And actually, give me just a second. It kind of feels like the air is not on, so I don't want anyone getting a heat stroke in here. So let me text someone in facilities to come by and see if they can start the air here. Okay, so hopefully they can come soon. Yeah, so I don't want you guys to pass out. I don't want to pass out from heat exhaustion up here. Okay, all right. So the way we use this for Green's theorem is that we mostly, we computed both sides, right? So we learned how to compute line integrals. We learned how to compute the double integrals of the curl, right? And we showed that they were equivalent, right? So for divergence theorem, we're mostly just gonna be focusing on this side, right? Because what you'll see very soon is that, the triple integral of the divergence is much, much easier to compute Okay. We'll talk about the surface integral a little bit, right? Mostly we're going to talk about, what the surface integral actually represents. But we're not actually going to do anything in detail. We're not going to compute it, because that's a little bit too cumbersome for this class. Okay. So let's talk about that. So let's talk about, not the computation of a surface integral, but the physical interpretation of what a surface integral represents. Okay. All right. So let me go ahead and draw. Let's write out our expression for the surface integral one more time. So the surface integral that we use for divergence theorem is specifically the surface integral on a closed surface. But we'll talk about just surface integrals just in general here, and then we'll talk about what it means to be a closed surface first. Okay. All right. So let's kind of break down this integrand here and kind of see what it's representing. Okay. And so on the one hand, we have our f here, where f right here, this is a typical vector field. Okay. So it's a vector, vector quantity that is that varies in space, right? So it's a multidimensional function with multiple components. Okay. Right. And this n hat here, this n hat is what we call a surface normal vector. Okay. Okay. So for every surface that you have, and this is not just including in here, but just for any surface that you define in a mathematical sense, we can always define what's called a normal vector to that surface. Okay. So let's say that, we have let's say we have a surface that kind of looks like this, right? Right. So we have this kind of like almost like bed sheet looking surface, right? So at every point on this surface, we can define a normal vector that is it's perpendicular to that surface itself. Okay. Right. So a normal vector would look something like that. So it's pointing directly outwards. And if you have a surface here that has some kind of curvature, the direction of that normal vector is going to change depending on where you are on that surface, right? So let's say, at that location, the normal vector points straight up, right? But if you can imagine that this surface here has some curvature, right? Over here, the normal vector may point kind of slightly to the right, right? As it kind of conforms to the surface. Right? Over there might be point slightly to the left. Okay. Okay. But one way that we define our surface is that we have to parameterize or define what the normal vector looks like. Okay. Now, if we were to kind of go through and learn how to actually compute surface integrals, this would be one thing that we have to parameterize, one thing that we have to quantify. Let me say parameterize. That's probably the word for it. Okay. right? So just like we saw with line integrals where we had to parameterize our curve, right? So for surfaces, you have to parameterize the normal vector. That's not the only thing you have to parameterize, but it is one thing that's important, okay? The details of that, you know, for our purposes is not too important. What is important is the fact that, you know, this normal vector is always going to point, you can think of it as pointing away from the surface. Okay. Right. Hence the name normal vector. Okay. So now that we have kind of an understanding of what that normal vector represents, right? Let's go back to our surface integral here and kind of interpret kind of what's going on, right? So if you look at this expression, right, we are taking the dot product between our vector field and this normal vector. Okay. Right. So what does dot product mean, right? So you take the dot product between two vectors, right? You have a vector field and a normal vector, right? The dot product essentially is going to tell you how well those two vectors are aligned, just like we saw with Green's theorem. So the way we can interpret that is that, you know, when you define a surface to do a surface integral for, right, that surface is going to exist within the same, you know, space as our vector field. Okay. And so if I were to come down here, right, we have this surface, right? There's going to be some vector field that's going to be going around in the background, right? So our vector field, you know, may look something like this. Right? So our blue lines here, that represents our vector field. Okay. Right. So with that fact in mind, the fact that we know our vector field and our surface exist in the same place, and we take the dot product between those two vectors, right? And we know that we're taking an integral. That means we're summing up all the contributions from this dot product. Okay. Right. So let's write all that down. So knowing that F and surface exist in the same place. Okay. Right. Right. Essentially, what we're doing with the surface integral is we're seeing how well does our vector field pass through our surface at all points in the surface. Okay. Okay. Because if our vector field is aligned with the normal vector and the normal vector points, you know, out from the surface or points through the surface, if those two are aligned, right? So if F and the normal vector are aligned, that's going to give us some positive value or negative value if they're kind of opposite aligned. And if we sum all those up with an integral, right, that surface integral is going to tell us how well aligned those two vectors are. Okay. Now the opposite case is, you know, let's say that we have a surface that is completely parallel to our vector field. So let's say that we have a surface that kind of looks like this. And I apologize, it is a little bit hard to draw in 3D. Okay. Right, so let's say we have kind of a vertical wall like this where our normal vector kind of points down like that, but we have a vector field that points completely parallel to it. Right? So let's say our vector field kind of just points up and down just like that, right? So if you took the dot product between these two quantities, right? So we take the dot product between the vector field and the normal vector. In this case, since our two are perpendicular, their dot product is going to be 0. Okay. And if their dot product is 0, that means the surface integral of this vector field on that surface is also going to be 0. Okay. Right. So this kind of brings up kind of the way that we typically use surface integrals in engineering applications, right? So a lot of times when we're computing surface integrals, the surface that we define is kind of almost like an imaginary surface. It's not really a physical object, but usually we define surfaces in a way where we want to find out how much our vector field is passing through a certain point. Okay. And so this has a very specific name in engineering. So we call this a flux. Okay. So you'll come across the term flux, in your other engineering courses, heat flux, fluid flux, electromagnetic flux, right? So when you talk about flux, you're talking about how much a vector field passes through a surface, right? So I'll give you an example. So, and it's another example from fluid mechanics. I apologize. That's just my background. Okay. Right. So oftentimes in fluid mechanics, we're interested in seeing, if you have kind of a complex fluid flow situation. So let's say you have, you have water that's running down a river or through a creek. You want to find out how much mass flow of water is passing through a particular point. Okay. All right. So let's say that, we have a stream of water like that. Okay. And let's say that, for some reason, maybe you ran a simulation or something, the velocity field for the water, right? You want to find out how much of that water is passing through, let's say a critical juncture in the river, maybe right before it splits or something like that, right? And so what you would do is that you would draw kind of an imaginary surface, right? Like this, right? Right? And then if you compute the surface integral, or sometimes, I often call it the flux integral. If you compute the flux integral of the water passing through that surface, that's going to give you a measure of how much mass flow of water is going to be passing through that particular. Okay. Okay, so that's the idea with the surface integral. So, again, we're not actually going to be computing these surface integrals, but it's important to understand what they represent, so that when we're using the divergence theorem, it becomes a little bit more. Okay, any questions on this? Okay, so with that said, let's see how we actually use divergence theorem, right? Okay. So let's write out the divergence theorem one more time. So divergence theorem, right, is the surface integral of a vector field on a closed surface. is equal to triple integral of that same vector, the divergence of the same vector field on that same domain. Okay. By the way, I've been checking my phone to see if facilities is going to come. They're ignoring my text. So if you ever feel lightheaded or anything, you need to step out, get drink water. Please, you don't have to ask. Just step out. Remember everything here is recorded, and I do plan on finishing this lecture. So your guys' don't pass out here. So your guys' health is more important than the lecture. Okay, so stay hydrated. Take breaks if you guys need to. Okay. Okay. All right, so the divergence theorem basically is saying that if we have a surface integral, we can transform it into a triple integral, right? The big caveat here is that our surface here that we're using for the divergence theorem has to be a closed surface. So we discussed what it means to be a closed path last time when we talked about Green's theorem, right? So a closed path is one where you start and end in the same place, right? And that had implications for our interpretation for Green's theorem, because if you start and end in the same place, the path that you create is essentially kind of like a circle, right? So a closed surface is a little bit more difficult to interpret because it's not exactly a path that you walk through space, right? So a closed surface is one that encloses a finite amount of volume. Right? So there should essentially be an inside portion of your volume or your domain, right? So we can say that that's going to be the inside portion. Okay. All right. So just some examples. So I think the concept of a closed surface is a lot easier to visualize than I think it is to kind of explain. So let's just kind of give some examples to see what this is, right? So the one that you're going to see most often for your problems is a box. Okay. Right. So box obviously is a closed surface, right? So there's kind of walls on every side, and we can say that inside the box we have a finite volume. Okay, so this is closed. Okay, another example of a closed surface would be like a sphere. Okay, right. So the inside of the sphere has a finite volume, and so we say the sphere is also a closed volume, closed surface. Okay. Right. An example of a non-closed surface would be something like a bowl. Okay. Now you could close the bowl, so you can put a lid on the bowl and say that that lid is part of the closed surface. But if you have an open bowl, and so you're only talking about just kind of the bottom portion, right? This would be an open surface because there's a portion here that's not closed. Okay, so just kind of remember that caveat when you're using divergence there. It has to be a closed surface. Okay. Okay. But according to this, if we if we have divergence theorem, then we can avoid taking a surface integral, and we can just do the triple integral instead. Okay. Okay, so let's do a quick example to show how this works, and you'll see it's actually much simpler than you may think. Okay. Okay. So these problems with divergence theorem and Green's theorem, I may word them in this way, but just know that you can use Green's theorem, you can use divergence theorem to convert it, right? Because in these situations, I'm only interested in just the result, but how you get the result is it's kind of up to you. Okay, so you may see problems that look like this. So may actually more specifically maybe look like this. So let's say evaluate the result of this surface integral. Okay. So let's say that we are want to evaluate the result of this surface integral right here. So we have double integral of x cubed dy dz plus x squared y dz dx plus x squared z dx dy. Okay. Okay. And we'll say that we want to evaluate this surface integral on the box defined by 0 is less than or equal to x is less than or equal to 1. We'll say in the y direction, we're between 1 and 2. And in the z direction, we'll say we're between -1 and 1. Okay, so you'll be given a problem like this. And so it would say evaluate the result of this surface integral. Okay, so if you take this at face value, you would say that okay, I would need to know how to do a surface integral. And you can see that we have a box, right? Right. So for this box, it would look something like this, right? So the x direction, this would be x is equal to 0, x is equal to 1, right? For the y direction, this is y is equal to 1, y is equal to 2. And the z direction, we have z is equal to -1. And then in the z direction, this would be z is equal to 1. Okay. Now, if you were to do the surface integral, right? Think back to the last example we did with Green's theorem, right? So boxes and rectangles are really nice to perform double integrals and triple integrals for, but they are a pain in the butt to do line integrals and surface integrals. Okay. So just like our rectangle, right? Each surface of this box is a separate surface integral that we have to do, right? Okay. So remember when we did our line integral on a rectangle last time, right? So on a rectangle, we have 4 sides, right? Each with a separate path, right? And so that requires 4 different line integrals. For a box, this is going to require 6 different surface integrals, because the box has 6 different surfaces, okay? Which is, of course, not impossible. You definitely do it. It's just, there's probably better uses of your time than doing something like that. Okay. So for a problem like this, where it's just asking you to evaluate the result, before you do that, it's better to convert this to a triple integral using our divergence theorem. Okay. All right. So how are we going to do that, right? Because actually the form of this integral here is actually not super convenient, okay? But we can actually pick out the components of our vector field from the expression that we have here in the surface integral, okay? Okay, because in particular, right, so we have this part here, x cubed dy dz. So this x cubed here, this is going to be the x component of our vector field because it's multiplied by dy dz, okay? This x squared y, this is going to be fy, the y component of our vector field. And then our z component is going to be this last part here, the x squared z, right? And so before we compute the divergence, right, because to compute divergence theorem, we need to compute the divergence of f. Let's first write out our f in its component form, just for completeness. Right, so f is equal to fx Fy, Fz, all the components. And so we plug in for those, we get x cubed, okay, x squared y, and then x squared z. Okay. Right, so it does help to kind of write out the components like this as you're computing the surface integral, just to kind of help with your calculations. Okay. Okay. Next, let's compute the divergence. So divergence, we're going to have take our nabla dot product with f. Okay. So remember, our nabla operator is all the partial derivatives in each of the particular directions. So we have partial x, partial y, partial z. Okay. Dot product with our f vector that we just defined right here. So dot product with x cubed, x squared y, and then x squared z. Okay. All right, so let's go ahead and evaluate this dot product. And so we're going to have partial x of x cubed plus partial y of x squared y plus partial z of x squared z. Okay. So luckily, this is actually a fairly simple expression here. By the way, this is modified from the notes, and so in the note, the surface integral that I have you compute in the lecture notes was actually for a cylinder. But on the homeworks, I only asked you to do boxes, and so I wanted to do an example with boxes just to kind of show you. Boxes are a lot simpler to do as well, right? And if I ask you this on an exam, I would only ask you to do it for a box. So we're kind of skipping through this a little bit just to kind of get to Fourier, just because we are a little bit behind. So I just want to make things kind of as simple as possible. Okay, so we evaluate all these partial derivatives. Partial derivative of x cubed with respect to x, that's going to be 3x squared, plus partial derivative of y of x squared y, which is going to give us an x squared, plus partial derivative with respect to z of x squared z, which is x squared. Okay. So we add these all up, we get 5x squared. Okay, now we're going to compute the triple integral of this 5x squared on our box. All right, so we have integral of 5x squared. Okay, so I left a lot of room there just so we can write the bounds of our integral. And so since we are integrating in Cartesian coordinates, we're going to integrate dx, dy, and dz. All right, so let's go ahead and put in our integration bounds. And so we have our integration bounds given to us directly from the box, right? So our integration bounds are all of these quantities here. So for the x integral, we're integrating between 0 and 1. So let's go ahead and put that in, right? So our x integral is the first one up. So that's going to be integral between 0 and 1. Okay. Our y integral is next. For y, we're integrating between 1 and 2. Okay. So that's going to be an integral from 1 to 2 with respect to y. And then for z, we're integrating between -1 and 1. -1 and 1.
Because of symmetry, you can just multiply by 2 and 0.
You could. Yeah. So in this case, there's no dependence on y or z. So you can actually just do those first, right? And so when you integrate with z, you get multiplied by 2. You integrate with y, you just multiply. So yeah, you can definitely. Okay, all right, and so let's go ahead and do this integrals. I'm just going to go from the inside out, and so if you're kind of savvy with integrals, you can do the y and z first, and those are pretty easy. But I'll just go inside out just because that's the traditional way. Okay, so we integrate with respect to x first, so we get 5 divided by 3x cubed, evaluated between x is equal to 0 to x is equal to 1. Okay, and we still have our y integral and our z integral. Okay. All right. So we evaluate these bounds, we get 5/3 times 1 cubed minus 0 cubed. And so that's just a 5/3. Okay. So we have integral from 1 to 2 of 5/3 dy dz, integral from -1 to 1. Okay. And so the rest of this is very simple. There's no dependence on y or z anymore. And so we integrate with respect to y. We get 5/3 times y, evaluated from y is equal to 1 to y is equal to 2, dz. Okay. Okay. We plug that in, we get 2 minus 1, which is just 1. Means we have integral from -1 to 1 of 5/3 dz. Okay. Right, and so then we get 5/3 z, evaluated from -1 to 1. Right. And that gives us 10/3. Okay. Okay. So for box domains like this, it's usually much more convenient to do the triple integral, and that's all that I would expect of you guys as well. Okay, so the last two problems on the homework are basically very similar to this. So just kind of it's going to tell you to compute the triple integral, or it's going to ask you to compute the surface integral. Just convert it using divergence theorem to the triple integral, and then it should be a fairly straightforward calculation. Okay. All right. Any questions on this example? This example here. Okay. All right. So the last thing I want to discuss before we move on to Fourier is the physical interpretation of our divergence theorem. Okay. So just like with Green's theorem, there is an important physical interpretation in terms of why these two integrals in particular are equal to each other. Okay, so once again, let's write out our divergence theorem again. All right, so this one's actually quite interesting, and it's not kind of what you expect, right? So let's start with the left-hand side, right? So we've already kind of talked at length today about what a surface integral represents, but we didn't really talk about what happens if you have a surface integral on a closed surface. Because one thing that's actually very interesting. So we talked about when you have a vector field that's aligned with the surface normal like this, right? Okay, so there's our surface normal, and let's say that you have a vector field that's kind of passing through it, right? Right. We know that when you take the dot product between the two vectors like this, where they may not be 100% parallel to each other, but they are very closely aligned, right? You should get a positive number because n and f share components that go in the same direction. Because f and n are aligned, they're going roughly in the same direction, you should get a positive. Okay. Now, what happens when they're in the opposite direction? So let's say that we have a situation. So let's say that we have maybe the other side of this surface. Our normal is looking like this. Okay. Our f is roughly going in the same direction. Again, may not be 100% aligned, but they do have components where we expect the dot product to be non-zero, right? Because they're not perpendicular to each other. Okay, and so in this case, the dot product because F and N are kind of roughly pointing in opposite directions, so they're roughly parallel, but in opposite directions, we actually expect our dot product to return a negative number. So it's a relatively small detail, but it is one that actually has big consequences, right? Because remember, our divergence theorem here, we require that our surface integral there be on a closed surface, right? And so let me draw kind of an example of a closed surface. Right? So let's say we have kind of a sphere that looks like this, right? Right? So for a closed surface, on one side of the surface here, we have our normal that may be going in that direction, right? And we have another normal on the other side that may be going in that direction, right? Remember, the normal always points out from the surface, right? And so all around the surface here, you're going to have normals that point in, whatever direction points out from the interior of the surface, okay? Okay. And then if you have a vector field that kind of passes through that like this, right? What's going to happen in this situation? On one side of your surface, you're going to have your dot product be negative. Okay? Right? So on the left-hand side of this, because our surface normal is pointing roughly opposite from the vector field, we expect our dot product to be negative. And on the other side, we expect it to be positive because they are roughly pointing in the same direction. Okay. So when you have a closed surface and you have basically normal vectors that kind of point in almost every direction, a lot of times when you compute the surface integral on a closed surface, you're going to get a cancellation kind of effect where, the positive flux on one side is going to cancel out the negative flux on the other side.
That's interesting.
Exactly. Yes. So it does. So, you'll get perfect cancellation if your geometry is perfectly symmetrical and your vector field is roughly constant, right? And so whatever comes in essentially is going to come out, right? Even for a surface that's not symmetrical, there is going to still be some degree of cancellations. It just may not cancel out completely. Okay. But actually, more importantly, is that the situations where you get a non-zero surface flux on a closed surface actually have more to do with the surface with the vector field more so than the surface itself. Okay. So when the flux is non-zero on a closed surface, right? So you have a vector field that's passing through a closed surface, right? Where you have some degree of cancellation. If you get a total flux that's non-zero, what that essentially means is that your vector field is non-conservative. Essentially, what that means is that there's going to be an imbalance of whether it's going to be an imbalance of how much a vector field is going into your surface versus coming out, or there's going to be more imbalance of vector field coming out versus coming in. Okay. So that sounds more scary than it has to be, but I'll give you a very, very simple example. Okay. Right. So let's say that we have a cup, like a cup of water. Okay. So even though the cup of water is not strictly a closed surface, right? The top is open, we can put an imaginary lid on it. So let's say that we kind of close the surface by putting an imaginary surface on top. Okay. Okay. So let's say we're going to fill this cup of water. So let's say that we have, we're going to put it under our tap, right? And we're going to fill it with water. Okay. And if we close put an imaginary lid on this, where we're not actually physically closing the lid, but we're putting an imaginary surface there so we can compute flux, right? We have a situation where we have way more, vector field coming in and no vector field coming out. Okay, so in this case, our vector field is represented by our stream of water. Okay, so our vector field goes in this case, but does not come out. Right, so this would be an example if you computed a surface integral on this cup of water on all of its surfaces, right? You would get a non-zero value because you have more water coming in than coming out. Right, right. But physically, what's happened, right? So physically, what we can say is that the reason this is because the cup is just filling up with water, right? So the amount of water in the cup is increasing as you leave the tap on. Right? Okay. So how does this relate to our divergence theorem, right? So we've kind of looked at the surface integral side. Now let's look at the triple integral side, right? So the triple integral side of our divergence theorem is this triple integral of our divergence. Okay. Now the divergence, right? Divergence is a very interesting quantity, but one way that we can interpret it is we can interpret it as kind of the how much density of our vector field is contained within our domain. Okay, so the divergence of F represents just got a text. They said that they said they turned the air on. I can kind of feel it. So hopefully it's getting cool with you guys out there. All right. And so when you take the triple integral of essentially our density, right? We're basically getting a measure of how much the density of our vector field is changing within our ball. Okay. Or I should say we're summing it up. Okay. Okay. And so with all of that kind of knowledge in mind, we kind of come up with a very kind of succinct kind of statement that divergence theorem expresses, right? So divergence theorem essentially expresses this kind of simple idea where if you have an imbalance of flux going into a domain, or I should say any imbalance right? So let's say you have more vector field coming in than coming out, or more vector field going out than coming in, right? Any imbalance of flux that you exhibit will result in a change in the amount of that vector field within your domain. Right? We can say result in a change of density. Right. So that's essentially what our divergence theorem is expressing to us. Okay. Or if you come back to that the water filling example, right? A change in density means that the water is filling up the cup. Okay. So the amount of water or the density of water within the domain is going up as we're filling the cup, just as divergence theorem kind of shows us. Okay? All right. Any questions on divergence theorem? Okay, all right. So that's everything with vector calculus, and so that's everything you need for homework 4. I know it's cutting a little bit close. I know it's due tomorrow, but hopefully the last problem is doesn't take you too much time after today. Okay, there might be a conceptual question with divergence theorem as well. Right? Okay, so we have about 20 minutes left in class today. Let's start our discussion of Fourier. Let's kind of just introduce the idea of what it is, and then of course we'll dive more into it next week. Okay, so there's actually two parts to our Fourier topic here. So there's Fourier series, which I think is the part that I think most people associate with Fourier, and there's the Fourier transform, which we'll talk about after spring. Okay, so let's start with the Fourier series. All right, so like I mentioned kind of earlier in class today, we're at the part of the semester in 308 where we see huge shifts in terms of the topics that we cover, right? So Fourier series really has absolutely nothing to do with vector calculus, and so we're kind of really changing gears here, but it's something that we kind of have to cover in this class. Okay, so for Fourier series, we are looking at analyzing periodic functions. Okay, so what is a periodic function? A periodic function is simply just a function that repeats itself repeatedly over and over again until infinity. Okay, so what are some examples of periodic functions? So the very classical periodic functions are your sinusoid, so sine and cosine. Right, so we have sine of t, right? We know what that looks like, right? So sine of t looks something like this, right? So sine of t is a function that has this, kind of oscillating structure. It goes up and down and repeats the same pattern over and over. So we saw this in our, mass spring damper solutions, right? So if you have an undamped oscillator, this is the solution that you get, right? But sine is a very classical example of a periodic function, okay? It's not the only periodic function, so there's cosine as well. But we also can make periodic functions out of almost anything, okay? So the idea with Fourier series is to give us a way to basically analyze these periodic functions, okay? So that's kind of our goal here. Okay. Right. So why would we want to do that? Why are we interested in analyzing periodic functions? Well, there are a lot of applications for periodic functions in engineering. Okay. So I would say the most obvious application, the one that you're going to see this the most, is in signal processing. Okay. So when you are, and this is obviously a topic very much in the realm of electrical engineering, computer engineering, right? So a lot of times when you're looking at the electrical signal that's coming from a particular device, right, it's always going to come in as a periodic function with a specific frequency with a specific amplitude, right? And so understanding Fouriers and Fourier transforms and Fourier series is very crucial to understanding how signal processing works, okay? Another important application is vibrations. Okay. Particularly resonant vibrations. Okay. Right. And so if you were to measure, if you were to take a physical object and, measure its vibrations, it's going to appear as a periodic function. And so having different tools to analyze this in terms of frequency and amplitude is going to be important for our understanding of that. Another really interesting application, and the one that we'll actually focus on a lot, throughout this discussion, is the idea of acoustics. So acoustics is essentially sound design of a physical space. Okay. Because what we interpret as sound, right? So basically the sound of my voice that's kind of going through this room, that's being broadcast on Zoom, is essentially just fluctuations in air pressure that's traveling through the air to your guys' eardrums. Right? So understanding a good understanding of acoustics just necessitates just a strong understanding of Fourier series. Okay. All right, so basically any application where you have kind of an oscillating signal or an oscillating kind of response, Fourier is a very important skill for that. Okay. And in fact, there's a very commonly used engineering tool that you may have used in a previous class already. In MATLAB, it's called the FFT. So FFT stands for Fast Fourier Transform. So that is kind of a very important topic, and we'll get into that a little bit kind of later on as well, in terms of what that computes and kind of what that represents for a particular function. Okay. Okay, so that's where we're going to go with Fourier. I know very different, has absolutely nothing to do with vector calculus, but important all the same. Any questions kind of before we kind of dive into this? Okay. All right, so to start our discussion, let's talk about the concept of sound and acoustics, and how that relates to our discussion of Fourier. Okay, so like I just mentioned, what we perceive as sound is nothing more than just, essentially just pressure waves that are traveling throughout the air. So the concept of sound and the concept of hearing is actually fascinating because our eardrums, our eardrums are actually very, very sensitive organs in our body because they're able to kind of pick up these very minute kind of fluctuations in the air pressure and then transform that into an electrical signal that we interpret in our brains as right. So very, very fascinating. Right. And if you really want to get into the details of this, acoustics is a very, very rich, very, very kind of complex field. There's a lot more to it that we can talk about here. But just to start out, we're going to break this down to kind of the two simplest components of sound. And so one component is the volume. Right. So volume, I think, is generally what a lot of us are familiar with, right? So that's how loud a sound appears. Okay. And the other kind of component of sound is its pitch. Okay. Right. So the pitch is the way we kind of characterize it as kind of the character of the sound, what we interpret. Okay. So these two concepts here actually lead directly into our discussion of Fourier, because they're going to lead into concepts of amplitude as well as frequency. All right. So let's talk volume first. So volume, the way we kind of interpret volume is, we interpret that as kind of how loud a sound is, right? But more specifically, in kind of engineering terms, volume is a description of the intensity of a particular sound. So loud sounds sound very, very intense. They're very harsh on our eardrums usually. It's usually not what we like to hear. And very soft sounds are very, low volume sounds are very kind of quiet, but sometimes they're so quiet that it's hard for us to pick it up. Okay. Physically, the way that volume actually manifests itself in our sound waves is based on the amplitude of the wave. Okay. All right. So let's do kind of two examples here. Okay. Okay. So let's look and kind of see an example of what a loud sound would look like versus a very quiet sound. Right. So on our two axes here, our horizontal axis will be time t. Right. Vertical axis will be air pressure. Because remember, sound is nothing more than just kind of fluctuations in air pressure that are traveling through space. Okay. So for a very loud sound, you may have very, very high amplitude waves, right? Where the amplitude, remember, if you kind of remember from previous class, the amplitude of a wave is the distance between the peak of the wave and the horizontal axis, right? Or the difference between the peak and the average value. Now, there's different ways to describe amplitude. Some people describe amplitude as the peak to peak. And so that's kind of the difference between the absolute peak and the absolute min, right? Some use a different color, right? So some people might say that this length, right? So the absolute distance from the absolute max and the absolute min, right? So I would call this the peak to peak amplitude. right? So you can think of, some examples of very loud sounds. And so like a very loud engine that might be revving up. Maybe you turned on the radio way too loud, right? So that's kind of what this would look like, right? In my case, this is my wife when she's snoring at night. It's extremely loud. It wakes me up at night. So we're about an hour and 5 minutes in, so I don't think my wife will see this. So I can say that. Sometimes she watches my lectures, but I don't think she gets this far. Okay, so that's what a loud sound would look like, right? So we have very large amplitudes. A soft sound would be the opposite. So a soft sound would be very, very low amplitude. Right. So you can see for these two waves here, the frequency is about the same. And we'll talk about frequency again in a second, right? But the big difference obviously is going to be the amplitude. So what our ears kind of perceive as sound, right? So whether the loudness or the intensity of the sound, really kind of it all just depends on the overall amplitude of the pressure wave. Okay. Okay. So if you want numbers for this is just trivia, right? So typical sounds. Typical sounds that we kind of, as humans kind of experience on a daily basis, they have a pressure amplitude of about, it goes in between, 0.000002 to 2 pascals. So very, very small, right? So it's not something that can be picked up with the normal kind of, air pressure monitor. It's not something that's going to cause the needle to move there, but it is enough to kind of, make our eardrums, pick up on sounds. Okay. Okay. So a little bit more trivia, right? So, you always kind of hear talk of, don't expose your ears to loud sounds over long periods of time because it could cause damage to your eardrums, right? So that's true. So if you expose your ears to, pressure amplitudes that are greater than 20 pascals, that's generally the range where you start to see some damage. Okay. And so one of the loudest sounds like ever kind of officially recorded in history was the sound of a volcano eruption in Indonesia in 1883. I'm actually quite surprised that they had instruments that measure sound that precisely back then. But for this case, it was so loud that it's not too surprising that they were able to measure. So that volcano measured in about 100,000 pascals of pressure amplitude that could be heard even about 5,000 kilometers away. Yeah. So if you're basically anywhere near that volcano when it erupted, you were going deaf. Your ears were destroyed. Right.
You say near, how near?
I'd say anywhere between, probably like anywhere between like 10 kilometers of this, you're probably not hearing again. But you also might also not be in good shape because the volcano erupted and you have lava that's coming at you very quickly too. So yeah, generally not a good idea to be near a volcano when it's erupting. Yes.
What about fine whistling sounds that are very quiet but still cause ear bleeds or still cause just put people down?
That's a good question. So in those situations, those whistles are, they're producing a very loud sound, but they're producing at a frequency that actually is, doesn't actually cause like a signal that goes to your brain. So you don't actually hear it, but the pressure waves are still there. And so that's still enough to kind of, cause damage to your eardrums. It's just you don't really perceive it as sound unless it's like a very, you only really hear kind of a very, very high pitch because your ears are not tuned to that high pitch sound.
So it's not terribly dependent on resonance. It's just
so your ears can typically pick up a certain range of frequencies. And so, outside of that range, there still might be fluctuations in air pressure that are there. It's just that your ears can't really pick it up or it can't interpret it as sound, right? So your brain doesn't interpret it as that. But it's still causing your eardrums to react, right? It just doesn't register as a signal. So in those cases, those would be situations where the frequency is too high to perceive, but your eardrums are still reacting to those pressures, and that could still cause damage. Yeah. All right, but typically, when we talk about the volume of sound, we don't typically talk about air pressure magnitude. We use a unit system called the decibel. Named after a person. Okay, but the way that decibels are actually computed is actually based on the air pressure. Right? So the decibel rating. Okay, so LP here. This is our decibel rating of sound volume. Right. It's a log-based measure, and so a decibel of if you go up in decibel, that's basically a change in magnitude, right? So it's 20 times log base 10 of the pressure amplitude of the particular sound divided by a reference pressure. Okay. Where the reference pressure is, basically the typical pressure for a typical sound. Okay. Which I think officially they use a number of 0.000002 Pascal. Okay. So kind of the typical pressure amplitude of a fairly soft sound. And so basically the greater amplitude of pressure of the sound is going to lead to a greater decibel rating, but it's a log-based measure, right? And so just like the Richter scale, so just like earthquake magnitudes, if you go up in one, right? So you go magnitude 3 to magnitude 4, right? That means that your earthquake was 10 times more powerful from 3 to 4, right? So decibels is kind of the same. So it's one of those measurements that I think is generally hard for people to kind of interpret. But the reason we do that is because there's such a huge variation in sound volumes that can occur. And so we have to use a log-based measure. Otherwise, we're talking about orders and orders of magnitude difference. Okay. All right. Any final questions before we wrap it up for this week? Okay. All right. That's all the time we have for this week. If you haven't picked up your exam yet, I have it here. So please pick it up. Today will be the last day I bring it to class. And so if you don't pick it up after today, it will be in my office. And so you have to come to office hours or just arrange a time to meet with me. All right, so thank you guys for coming this week. Hope you guys have a good rest of your day. Have you guys have a good weekend, and I will see you guys next week. Yep.
and for the honor society thing, that's all the information is just gonna be in that email.
Yes, yeah. So there's a session, I believe, on the 24th next week. Yeah, so make sure, but if you can't make it in session, send Jessica an email. So Jessica's email address is at the bottom of that one. So it should be tvpca@gmail.com.
Maybe see.
Yeah, and then just send that an email and then just say that you're interested. You want to.
Okay.
Yeah,
sounds good. And then as far as the sending you that email, we always talk about
yeah.
I'll try it tonight.
Okay.
It's tomorrow. So
Yeah, that's fine. Yeah.
All right, thank you.
Yeah. Hey, yep.
Please.
Yep. You
Thank
can-
you.
Your cheat sheet is stapled on the back. Yeah. If you want to keep that for the final exam, just hang on to that.
Weekend, thank you.
Thanks, you too.